In this example, they want us to prove that this function has exactly one real root. So what we want to do is figure out how we're going to prove that. And first, so my plan is I'm going to show that the function has a root using intermediate value theorem. And then I'm going to show that the function can't have more than one root using Rolle's theorem. So what is this going to do for me? Using IVT, I'm going to show that it has a root. And then I have to show that it has exactly one. So I'm going to use contradiction and show that it can't have more than one. And if it has one but can't have more than that, then it has exactly one. So let's start by using intermediate value theorem. So by IVT, if the function is continuous from on the closed interval a to b, so from a to b, and if f of a is less than 0 and negative, and if f of b is greater than 0, positive, then there exists a number c such that the function value at c is 0. So remember we did this before using intermediate value theorem. We showed there's a negative. If there's a negative and a positive and the function is continuous, then there has to be a value between them. So if something's negative and positive, there has to be a value of 0 somewhere. And so looking at the function they gave us, we know that x cubed plus x minus 1 is continuous because it's a polynomial. And all polynomials are polynomial. All polynomials are continuous. And now we want to show that there's a negative and a positive. So just pick some numbers that would give you a negative and a positive. So for example, if I plug in 0 to this function, so f of 0, I get negative 1. So I've shown that f of 0 is less than 0. And pick some number that would give you a positive. So 1 gives us a positive answer. So if I plug in 1, I get 1. So that's positive. So f of 1 gives me something greater than 0. And so now I can say, because it's continuous, and because I have less than 0 and greater than 0, there is a c value. Thus, there is a c such that the value of c is 0. So I've just shown that this function has a root. And more specifically, I've shown that this function has a root between 0 and 1. It has a root between 0 and 1. Well, this wants me to show that it has exactly one root. So I've shown that it has a root, but it could have more than one. So now I have to show that it can't have more than one. So I'm going to use Rolle's theorem. So now I'm on part 2. Can't have more than one. So let's suppose that it has 2. Suppose that f of x has 2 roots, a and b. Okay, so if I'm going to say that it has 2 roots, then it should, if it has 2 roots, then a and b should equal 0, because a root means that it's crossing the x-axis. So that means f of a is 0 and f of b is 0. So let me say it again. If I'm saying that the function has 2 roots, a and b, then their y values must be 0, because that's what a root is. And so what I've just shown is that f of a equals f of b. And so remember, I'm using Rolle's theorem. So I've shown that f of a is equal to f of b. I also need to show that the function is continuous and differentiable. So we know that f of x is a polynomial, which tells me, thus, continuous all polynomials are continuous and differentiable. So I've shown that it's continuous and differentiable and that f of a equals f of b. So then by Rolle's theorem, there is a c. There is a c such that the derivative of the function at c is 0, because I've shown that f of a and f of b equals 0. So what are we going to do then? We're going to find the derivative of the function that they gave us, and we are going to set it equal to 0. So let's take the function they gave us, this x cubed plus x minus 1. We're going to find the derivative. Which is 3x squared plus 1. And if I set it equal to 0, I get subtract 1 to the other side, divide by 3, take the square root, and we get imaginary numbers. So what we just showed is that the derivative of x is greater than or equal to 1 at all times. That's why we got an imaginary number, and so the derivative cannot equal 0. There are no values that will give you 0. So f of x, thus f of x cannot have 2 roots. So we showed that 1, it has a root, and then now we just showed it can't have more than 1. So it has exactly 1 root.